All right, welcome back, everybody. Very sorry that I'm not there with you today. However, we're just going to keep on pushing through. So just kind of a rundown for the week. Today, we are going to do section 3-4. I'm going to try to give you the whole thing for section 3-4. Okay. And then on Tuesday, that will be a section 3-4 workday. So if you miss any part of the video or you want to watch part of the video over again, want to just work on it, that's totally fine. Wednesday and Thursday, we do section 3-5, which is definitely a 2-day lesson. Like I'll have to split it up into 2 days. And then on Friday, we're going to do a 3-5 work day. Okay, I believe so, at least. At least that's the plan. Okay, well, let's get to it. I don't want to make this video longer than it needs to be. It's already 10:30. Oh my gosh, jeez. Go to bed, Laverick. All right, the things I do for you kids. All right, so what we're going to be looking at in this section is the chain rule. The chain rule. So suppose I wanted to find f prime. All right, take a look at that function. Suppose I wanted to have f prime. You may think, well, okay, well, I know how to find the derivative of this. That's really just like taking x squared plus 1 to the 1/2 power, right? So, I mean, I'm tempted to just say, okay, well, maybe it's just 1/2 to the x to the, maybe I got to take the derivative on the inside. Maybe I got to do that. Maybe make it like 2x. Maybe it's 1/2 to the 2x. Maybe 1/2 times 2x. Maybe it's just x. You know, you might be tempted to try to just find the derivative of each piece. Oh, maybe, oh, I forgot that's x to the negative 1/2 too. So maybe it's, maybe it's this or something. That's not the case. But you might be tempted to just try to take the derivative outright. But what are we noticing here as we take this derivative? We're noticing here that we've got a function within another function, almost like it's composite looking, right? We got a function within another function. Differentiation formulas we've learned in the previous sections do not actually make us able to calculate this because we've got a function within another function. It's almost, yeah, it is composite, right? It's composite. In fact, what we have to do here is we have to let this inside function, this x squared plus 1, be a whole letter of it in and of itself. Okay, they call it u, and yeah, great job, authors. I really love the abbreviations that you're doing. Great job. I mean, we do understand that this book is made for, you know, kids that will laugh at that. So y, we're going to call it f of u. Great terminology. Fu is equal to radical u, right? So if we call f, that outside function, the square root, and then we take this x squared plus 1 and we call it u, then we can say that y is really equivalent to the square root of u. Well, what we can say here is that because we've got some composite looking function here, we can actually use this thing called the chain rule. So here is the chain rule. Here is the way that I believe you should write it down. We got the Leibniz notation down here, but I don't love that. So go ahead and pause and write this down. You do not have to write down the Leibniz notation though. Okay, so let's kind of analyze what we're saying here. So what we say here is that if you've got a composite looking function type thing, then you can take the outer derivative still of the inner function and then multiply it by the derivative of the inner. You kind of like peel away the layer. You got to take the derivative of the outer times the derivative of the inner. But don't forget that you leave the inner function in when you find the derivative of the outer. What do I mean by that? We'll take a look here. Let's actually find the derivative. So again, it's f prime g times g prime, right? That's the chain rule. We have to recognize that we have to do the chain rule because there's a function within another function. So our f is like the square root and our g is like the x squared plus 1. So we find f prime. Now remember that this is x squared plus 1 to the 1/2 power. So taking to the 1/2 power is really my f. So I'm going to take 1/2 of x squared plus 1, leaving the inner function in to the negative 1/2 times, okay, now I take the derivative of the inner. I peel away the layer of the 1/2 power and I get the 2x. Okay, Now, let's reduce that down. I take 1/2 of 2, and I get just x times x squared plus 1 to the 1/2 to the negative 1/2 power. You hear me flipping through pages here because I just got to check and make sure. Okay, good, yeah. And then we take the negative 1/2 power and put it into the denominator. The x stays in the numerator, so then I'll make it the radical here, x squared plus 1 into the denominator. And there we have it. There's the derivative. Okay, so the chain rule just peels back the layers and takes the derivative each time. Like here, this is just another explanation of it. Using the chain rule, we work from the outside to the inside, right? We have to peel away the outer layers to differentiate the inner layers. We take the derivative of the outer times the derivative of the inner. So let's just keep working with it. So consider these two different functions. Let's say y equals sine of x squared. And then we're going to find the derivative of y equals sine squared x. Notice that those are two different things, right? This is sine of x squared. This is sine of x squared, right? They're two different things. So what's my inner and outer pieces here? Well, my inner piece, this g, is the x squared. The sine is the f. So I take f prime g times g prime. F prime of g times g prime. So what is the derivative of sine? It's cosine. So cosine of x squared, leaving the g, f prime of g, times g prime. Peel away the layer of the sine, and we find the derivative of the x squared is 2x. So I would just rewrite this 2x cosine x squared. Okay. Just flipping. Okay, good. 2x cosine x squared. Yep, there we go. And then we do the same thing over here. However, now our f is our squaring the thing, and our g is the sine. So our derivative of the squared gives us 2 sine of x, right? 2 sine of x to the first, if I really wanted to, times the derivative of sine is cosine. And if we're being fancy, that's a double angle formula. That's sine 2x. I would totally be fine if we left it like this. But if we're being picky, that's a double angle formula. Look at it on the Mr. Delap's trig sheet, and you'd find it. All right, let's keep it going. So this is the power rule combined with the chain rule. Honestly, I just think about the chain rule. I don't know, trying to write it, formulate it like this. Just memorize the chain rule. F prime of g times g prime. Okay, there we go. Done. All right, so what is my f in this case? My f is taking it to the 100th power, and my g is my x to the 3rd minus 1. So peel away the layer of the f, differentiating x to the 3rd minus 1 times the derivative of g, which is just 3x squared. So in other words, 300 x squared, ooh, I forgot to the 99th power, oops, times x to the 3rd minus 1 to the 99th. I would have caught that on my key, but I bet there was somebody out there saying, well, Mr. Albert, with the 99th. Just gotta double check that. Yep. 300 x squared, x to the 3rd minus 1 to the 999th. All right, let's take a look at the next one. Okay, so let's kind of manipulate it down before we identify our f and our g. So what do I mean by that? I mean that this is really x squared plus x plus 1. It was in the denominator, so it's negative, and it's a cube root, so it's 1/3, right? That's our function. Okay, so our f for the chain rule is really the to the negative 1/3 power. Our g is our x squared plus x plus 1. So find the derivative of the 1/3, negative 1/3, leave g as it is, and then go down 1 unit, so negative 4/3 times the derivative of the inner, 2x plus 1. Okay. So all said and done, what's in the denominator? I've got a 3 in the denominator. This is negative. The 2x plus 1 stays in the numerator. And this is the cube root of x squared plus x plus 1 to the 4th power. And there we have it. Okay. Let's take a look at the next one. Let's find this derivative. So notice again, a composite-looking function. I've got a rational function with a exponent on it. So this is my f, and this is my g. I know this seems weird because now we've got a, well, I shouldn't get ahead of myself. So let's find g prime. G prime of t is going to be equal to, so derivative of my outer is 9t minus 2 over 2t plus 1 to the 8th times, well, I've got to take the derivative of my quotient on the inside. So this is a chain rule with a quotient rule in it, right? Low, d high, which is just 1, minus high, d low, which is just 2, all over low squared. So all said and done, this is really just 2t plus 1 minus 2t minus 4 all over 2t plus 1 squared. So 2t minus 2t will cancel. 1 minus negative 4 turns into a 5 over 2t plus 1 squared. Okay, so that is g prime, 2t plus 1 squared. Okay, let's see if we can, work this out a little bit more. 9 is in the numerator. I can distribute that t minus 2 power, that 8th power to the t minus 2 over the 2t plus 1 to the 8th times 5 2t plus 1 to the 2nd. Okay, so on the top, all said and done, I've got a 45. Yeah, 45 times t minus 2 to the 8th. And then look, I've got the same base, 2t plus 1s. So 2t plus 1 to the 10th total. There we have it. Okay, let's keep on rolling. Just a couple more problems to do. All right, so let's differentiate these. Notice that I've got a product rule right here, right? I'm multiplying this piece times this piece, but within each product, I've got some chainy looking things going on. So let's find the product. So it's, what did we say? I really don't want to go up there and get that. G f prime plus f g prime. I believe that's what it was on the formula sheet. Okay, so g, which is x to the 3rd minus x plus 1 to the 4th power times f prime. Now, when we take f prime, that's going to be 5, 2x plus 1 to the 4th times the derivative of 2x plus 1, which is 2. Okay. All of that plus f 2x plus 1 to the 5th times g prime. So g prime is 4 x to the 3rd minus x plus 1 to the 3rd times the derivative of the inner, 3x minus 1. Okay. So again, where is this 2 coming from? It was the derivative of the 2x plus 1. Where is this 3x minus 1 coming from? It was the derivative of the x to the 3rd minus x plus 1. So let's just reduce this down. It looks like I've got a 10 times 2x plus 1 to the 4th times x to the 3rd minus x plus 1 to the 4th plus 4 2x plus 1 to the 5th x to the 3rd minus x plus 1, 3x minus 1. I don't believe I can do anything else from that. I could pull out a 2x to the 4th and the x to the 3rd minus x plus 1 to the 1st power. Oh, did I forget it to the 3rd? Yeah, I did. To the 3rd. I could pull out that to the 3rd, that x to the 3rd minus x plus 1 to the 3rd. But really, that's not going to do anything. That's really not going to do anything. Okay, we'll leave it as that then. All right, differentiate y is equal to e times the sine of x. All right, so we've got, this is our f. Think about the inner and outer functions here, right? Think about the inner and outer functions. Our f in this case is going to be our e to the. Our g is the sine of x. So when looking at our f and our g, the first thing acting on x, our innermost function is sine. Our outer function is f, is that e to the x. Okay, so y prime is going to be, well, the derivative of f, which is e to the something. The derivative of e to the something is at e to that something. So e to the sine x, derivative of e to the x is e to the x, times the derivative of sine x, cosine x. And that's it. E to the sine x times cosine x. Okay. The last thing that we're going to talk about here is this chain rule to differentiate any b to the x. We have not come up with a rule for any type of function. We know the derivative of e to the x is e to the x, right? But what about 2 to the x? Or what about 3 to the x? What do we do there? Well, to understand what to do here, you have to think about the chain rule. Now, they go on this big tangent where they say, okay, well, we can let b be e to the ln of b, right? We can let b be e to the ln of b, because what does e to the ln of b mean? E to the ln is going to cancel, leaving just the base. So they're going to rig this up so that b is really equivalent to e to the ln of b to the x. Now, when I multiply, or when I take power to a power, I multiply. So this is really e to the ln of b times x. Now, how does that help us? Well, that's a chain rule. That's a chain rule. And if I'm differentiating with respect to x, that's not with respect to x. I can actually take that out. So take a look at what we can do here. So if I've got e to the ln of b to the x, well, I can take that e to the ln of b to the x. That's going to stay just like our e to the sine x did, times the derivative of this big piece. Well, the derivative with respect to x, not b, is just 1 times ln of b. Okay, so what was this equivalent to again? Oh, that's right. That was b to the x. So b to the x ln of b. What you guys have to know is that's our derivative. If you take the derivative of any exponential function, it's b to the x times ln of b. See, we wouldn't have understand this times the ln of b until we've done the chain rule. Like, why are we multiplying on something? Well, it's because of the chain rule. We might not remember how the chain rule actually worked it out, but now we can at least say, well, it's because of that. Okay, so 2 to the x, the derivative of 2 to the x would be 2 to the x times ln of 2. The derivative of 4 to the x would be 4 to the x ln of 4. And now think about it. The derivative of e to the x would be e to the x ln of e. Well, what is ln of e? It's just 1. So e to the x times 1 is just e to the x. It's another reason why the derivative of e to the x is e to the x. Okay, now this is not a exponential function, but what I'm showing here is that, look, I've got tangent within cosine within sine. This is like a chain in a chain, right? I'm actually chaining together 3 composite functions, or really, this is one big composite function with 3 parts, I guess we should say. So what I can do here is just keep taking the derivative and peel away the layers. So let's take the derivative of sine. Well, that's cosine of this piece all in there, cosine of tangent, times, and now we've peeled away the sine. Let's find the derivative of cosine. Well, the derivative of cosine is negative sine. So negative sine of tangent of x. Okay, we've peeled away that layer, times the derivative of tangent. Now, the derivative of tangent is secant squared. So we say times secant squared of x. Okay. And honestly, nothing's going to happen to that, because we got cosine of tangent of x. We got negative sine of tangent of x. We got secant squared x. There's no real formulas that are going to help us reduce that down at all. The only thing I could possibly do, and this is written in my notes, is bring the negative all the way up front, but that seems like a lot of writing to just move onward. It's 10:45. I mean, come on. All right, so y is equal to e to the secant of 3 theta. E to the secant of 3 theta. Okay, so I recognize the chain rule with the e to the secant of 3 theta. But what we need to see also is that 3 theta is in of itself a chain rule. Secant of 3 theta is itself a chain rule. Here's what I mean by that. Okay, so let's peel away the layer of the e. So e to the secant of 3 theta is going to turn into, okay, e to the secant of 3 theta because it's the exact same. Whoa, I forgot my 3 theta because it's the exact same thing, times the derivative of secant of 3 theta. Okay, the derivative of secant is secant tangent. So it's secant 3 theta times tangent 3 theta times the derivative of 3 theta, which is 3. So sometimes we forget about that numerical value on the inside that you have to multiply that back onto it because it's actually a chain rule. You got to watch out for that. So all said and done, this is 3 times e to the secant 3 theta times secant 3 theta. Oh, not, oops, sorry, not to the 3 theta. Secant 3 theta times tangent 3 theta. And there it is. All right, there's the chain rule, folks. Hope we're all having a good day, and I will see you all tomorrow.